Okay, welcome to Note Set 24, Section 5.3, looking at some applications of determinants, and this will be our last set of notes on determinants, and then we'll move on to eigenvalues and eigenvectors, which is probably the biggest thing that shows up inside electrical and computer engineering. So let's get on with this so we can get on to the eigenvalues and eigenvectors. So, we've spent a lot of time talking about how to solve this linear set of equations, ax equal to b. We've looked at, when they're solvable, when there's a unique solution, when there's infinitely many solutions, when there's no solution. And we've talked about the different ways of doing that, actual solution, primarily looking at, elimination, row elimination, things like that. But there is a cool rule that is based upon determinants, and it's called Kramers Rule. And it occasionally shows up. You may see in a course or in a textbook telling you to solve some set of equations by Kramers Rule. So you ought to know it, at least know about it. And so it's based upon determinants, and it comes about like this. So suppose, let's forget about ax equal to b for a minute. Suppose we take the identity matrix, we take its first column, and we replace it by the arbitrary vector x. So we'll just put x1, x2, x3 down that first column, so on. If you take the determinant of that resulting matrix, you should be able to puzzle out that the result will be x1. And you should also be able to puzzle out that if you were to replace the second column of the identity matrix by the x vector, the result would be x2 when you take the determinant, and so on and so on. Now let's set that idea aside. Now multiply that resulting matrix, I with the first column of x replaced, or with the first column replaced by x. So multiply that by a, and if you do that, you can puzzle out that the first column turns out to be ax, which, well, we know is supposed to be equal to b. So we know the b. So in that first column of a times this modified identity matrix, we can replace that with b. And if you further work it out, you can see that all the remaining columns of that product are just the remaining columns of a. So it gives us something that looks like this. Now again, we're setting something up. This is not what you have to do every time. This is just the setup. So we imagine taking A times, here's our modified identity matrix. We know that when we multiply A through, A will multiply each column. And when it does that, in the first column we'll get the B column, or the B vector, and then we get the second column of A and the second column of, or the third column of A. We're going to call that matrix B1. So it's B to remind us that it involves B, 1 to tell us that B goes in the first column. And that's the key idea behind solving these equations with Kramers Rule. So we're basically multiplying this thing column by column and figuring it out, what we get. Well, now we can take the determinant of these three matrices. Let me clear the ink off from here. So we've got A times this modified identity matrix is equal to B1. So we know that the determinant of this side must equal this side, but the determinant of the left side is the determinant of A times the determinant of this modified identity matrix but we already said you should be able to puzzle out, come on, there we go, should be able to puzzle out that the determinant of this matrix is just equal to x1. So the determinant of the left side becomes determinant of A times the single unknown variable x1 equals whatever the determinant of this is. Now there's nothing we can do with that. It'll depend upon what the specific B values are and the remaining A values. But what we can now do is say if the determinant of A is equal to 0, and remember that's the case when we're talking about a square system here. That's the case when A is invertible and we have a unique solution. So if we're trying to solve this, that better be the case. So determinant of A is not equal to 0, and so we can divide it and solve for x1. So here's a simple rule. You want to know the first element, you just form this B1 matrix, take its determinant, divide it by determinant of A. And then we can continue on. So that first component of x via Kramers rule is equal to that. We do the same thing or similar thing to find x2, except now we put this in the second column. B goes in the second column of this, so that becomes our B2. 2 tells us where to put the B. And again, we do the same thing. We get determinant of A is equal to, determinant of A times x2, which is the determinant of that matrix, is equal to the determinant of B2. And we solve that, and we get x2 is equal to determinant of B2 over A. And in fact, any one of these x's, all the way out to the last one, can be found by forming the proper Bn. And we say down here what that Bj matrix is. And so this is it. This is called Kramers rule. And one thing this does is it tells us the key role that the determinant of A plays in solving these. If the determinant of A cannot be equal or is equal to 0, we cannot solve this. So it shows the importance of determinant of A being non-zero. Another cool thing about this, where it may actually be useful, is suppose you don't really want to solve for all of these variables. So maybe you've got some circuit, if you're taking your circuits class or have taken it already. Maybe you've got a circuit. We've already mentioned that when you write your KVL and KCL equations, you write loop equation, mesh equation, or nodal equations. You'll get a n by n system where n is the number of loops, meshes, or nodes. So for a complicated system, you could get a lot of, fairly large number of nodes or meshes. But you may only be interested in solving for one of the variables, one voltage or one current. That may be the important one that you're interested in. And so you can do Kramers rule just to find just that one variable. So that might be a handy time to use this. Here's an example, simple 2 by 2 matrix. And so to solve this, we would have to compute 3 different determinants. We need determinant of A and then one determinant for each of the variables. But remember, if we only wanted to solve for one of the variables, if that was all we were really interested in, we could eliminate one of these matrices or one of these determinants. So you figure out what those determinants are, form the ratios, and there's your 2 solutions for this. So to completely solve an n by n system by doing Kramers rule, you need to evaluate n plus 1 determinants. But if you really only want one, if you're only interested in, what's x sub whatever, and that's the only one you're interested in for whatever reason, then you really only need 2 determinants. And that may be worthwhile doing it that way, especially if you can evaluate those determinants numerically. But if you're, in reality, these determinants are the sum of n factorial terms, which can be difficult. So it's really crazy to go about solving equations this way in general, but sometimes this rule comes in handy. Here's another example. We can extend this idea to be able to find the inverse. So basically what we're solving is A inverse is equal to I, and we're trying to solve for the inverse. So basically we're looking for two systems that share the same A, and so therefore we really only need 5 determinants, and so those would be the ones that we would need to evaluate. And the last 4 determinants are just D, negative C, negative B, and A, and those are the cofactors, and we get what we know is the answer for this. So no big divulgence of information in that example, just illustrating how one could use these ideas. And so that leads to a formula for the inverse. This is a general formula based upon cofactors. So we now have an explicit way of forming the inverse. And again, numerically, this is not really how we would have a computer do this. But like I said, sometimes it's kind of a handy thing to know. Now, the last thing we're going to look at in this section of notes is area, volumes, and their relationship to determinants. So we'll start off thinking about a triangle. So if I gave you the corners of a triangle in 2 space, in a plane, you should be able to figure out what the area of that triangle is. But we can use determinants to figure this out, and in some sense this is a much slicker and better way to go about doing it. So we'll see here that the triangle is 1/2 times a 3 by 3 determinant. Now we already alluded to the fact that a determinant finds the volume of the parallelepiped that's whose edges are defined by the columns of the matrix. So we can define this triangle this way. We've got 3 points, each having 2 coordinates, and so that would be the formula that you would use. And if you anchor any one of the points, but it's easiest to think about anchoring one of those points, x3, y3, if that were anchored to be 0, then we would get a 0 here and a 0 here, and we could use some of our previous ideas to show that this determinant boils down to this determinant. And if you want to see some derivations of why this is true, here's a couple links you can go to. What about going into 3 dimensions? So we've got a box that are defined by whose edges are defined by the vectors. So here's our A1, A12, A13. That's one vector that defines. So that's actually the first row. So the edges are defined by the rows of this matrix. I may have misspoken earlier and said columns. You can do it either way, really. We've got another vector here from the origin. This vector went from the origin, and this vector went from the origin. And it turns out that if you want to know the volume of that box, and let me say that the edges are not necessarily at right angles, so it's not necessarily a nice square or rectangular box, but the volume of this box can be found by the determinant of this matrix. So those are the 3 vectors are the edges, and we may have to take the absolute value of the determinant to get the volume, because if we get a negative value for the determinant, obviously volume can't be negative, so we have to take the absolute value of that. Now, if we look at a special case, clearly if we let these rows be just like 1, 0, 0, 0, 1, 0, and 0, 0, 1, we get the identity matrix. And we know that that defines a unit cube whose volume should be equal to 1. And we can check that this idea is consistent with that, because we know that the determinant of the identity matrix is 1, and that matches. So everything seems to be consistent. That doesn't prove it by any means, but it certainly is a nice check. When you're learning new things, you should kind of check to see that they're consistent with things you've learned already. So how about the shape and the volume of a 3 by 3 orthogonal matrix? So remember, the orthogonal matrix is going to have orthogonal vectors. We call the orthogonal matrix Q. That's just notational. And so we know it's another cube. And we know its volume is equal to 1 because orthogonal matrices not only have orthogonal vectors, but they are orthonormal. So how might this be different from the cube formed by the identity matrix? So if you want to think about that for a minute before I go and answer, and you might want to pause it, come back and hit play when you think you've got an idea. Well, so one thing is that you know that it's got to be a cube, but it's going to be rotated and mirror. It could be mirrored. Remember, we talked about rotation matrices are Q matrices. Reflection matrices are Q matrices. And the other thing that we talked about was that Q matrices take vectors and take a space of vectors and basically rotate and flip them, but keep distances and angles the same. So it'll be like taking this cube in your hand, anchoring one corner at the origin, so that and have the edges aligned with what you're envisioning as the standard axes. But now keep the one corner anchored and move the cube around any way that you want, as long as that corner is anchored. So you can just simply rotate it. You can revolve it around the axes. You can rotate it in place. Anything that you can do. You just can't squish it. You can't stretch it. You can't twist it so that it becomes deformed. So it maintains its cube form. It's just oriented differently. And so that's what all these different orthogonal matrices would look like, the cube whose volume they're trying to find. Now, how do I discover, or how do I prove that the determinant of an orthogonal matrix is actually 1, or potentially -1? How do we determine that? So again, if you don't want to look at your notes and you want to pause it here, try to puzzle it out, feel free, and then come back. Well, here's the hint. We start with the fact that it's an orthonormal, that they're orthonormal column vectors, and any orthogonal matrix has the property that its inverse is its transpose. And so Q transpose times Q is equal to I. Now that's the trick that we need. If we take the determinant from both sides, we take the determinant of this, and we know that that will be equal to the product of their individual determinants. So determinant of transpose Q, determinant of Q on the left, and on the right we have determinant of I, which we know is equal to 1. And on the left, we know that the determinant of any matrix is equal to the transpose of the determinant of the transpose of that matrix. So these two things are equal to each other. So let's just write it as determinant Q squared. And therefore, if we were to take the square root of this, we would get plus or minus 1 on the right-hand side. And that's why we get plus or minus 1 on that result. So we know that an orthogonal matrix is supposed to give us a volume of 1. And what's cool is that we can now use that to represent any, volume 1 cube, a unit cube, but it's had one corner anchored and the other corners can be moved around however we want them to be. So what if we were to take some rectangular, some box, doesn't have to be, square edges, right angles, and we just took one side of it and we doubled that length. Well, we would know from our experience with areas that the volume of that box should double. And what happens to the determinant? Well, that's going to be one row that gets multiplied by 2, and we had the row result that said you multiply any row by 2 and you will double the determinant. So that's all consistent. So this helps us understand that the determinant of A does indeed work like the volume of a box. So again, we're not proving these things. We're just showing that once we accept these ideas, they are consistent with things that we've done before. And like I said, that just comes from rule number 3 of determinants, which says if you multiply a row by alpha, you will get alpha times the determinant of the original. So now let's go back to the two-dimensional world and talk about area instead of volume. So there's a parallelogram. We've got two vectors, AB and CD, and we know the determinant of that is AD minus BC. So that's the area of that parallelogram. And now we can tie this back into what we saw at the beginning of this set of notes, that a triangle defined by those two vectors is going to be half of that parallelogram. So it's going to be half times the determinant of that. And you may need to involve an absolute value in this, depending upon where in the plane you pick those. Now, if you move the triangle away from the origin, we're back to what we saw in slide 6, which gives us this result when x3, y3 is equal to 0. And that's all we've got to say about determinants. So like I said, they're interesting little things, but they are not a super big idea. They are a key thing, knowing that the determinant cannot be 0 for the case when you want to be able to invert a matrix and solve uniquely for a square system. So they are important in that context, but the ideas and views that we've seen in the earlier sets of notes and the ideas that we're going to be seeing coming up are much, much more important than determinants. And look forward to seeing you in the next set of notes where we'll go into eigenvalues and eigenvectors.